So during last lecture, we have started this micromechanical behavior of lamina. Starting from previous lectures up till now, we have completed introduction, mechanics of material approach to stiffness, and in this mechanical material approach to stiffness or strength of material approach to the stiffness, here we started the assumptions. So particular assumptions we have seen, and with reference to that assumptions we have started to calculate the different values. So maybe in case of this micromechanical approach, we will need to take into consideration the properties of matrix as well as reinforcement. So both properties we will have to take into consideration. So here in longitudinal Young's modulus or transverse Young's modulus, in order to identify these properties or in the different directions, we are taking into considerations the properties and the assumptions. Is it okay? So yesterday we have seen what are the different assumptions. In that assumptions we have seen that the bond between fiber and matrix is perfect. Elastic modula, the diameters and space between fibers are uniform. Fiber are continuous and parallel. Fibers and matrix follows Hooke's law. Fiber possesses uniform strength. The composite is free from void. With reference to that, we have calculated the longitudinal Young's modulus. And finally, when we calculated the longitudinal Young's modulus, our equation which we get with reference to matrix and reinforcement material is E1 is equal to EF VF plus EM VM. Is it okay? So this particular Young's modulus which is calculated in the longitudinal direction. So with reference to longitudinal direction, what we say is E1 is the notation used for this, and EFVF plus EMVM, where EF is the Young's modulus of fiber, EM is Young's modulus of matrix, VF is volume fraction of fiber, and EM is volume fraction of matrix. So this particular equation is true for Young's modulus whenever it is in linear direction or longitudinal direction. Is it okay? With reference to that, we have solved one example yesterday's lecture. Before that, then transverse Young's modulus we have calculated with reference to this transverse Young's, because in longitudinal direction this was the direction which was considered, but in now this particular direction is the transverse direction. Sigma c whatever shown here, so that sigma c is in transverse direction. Is it okay? So we should understand first of all what is longitudinal direction and what is transverse direction, and with reference to this transverse direction, now what can be the Young's modulus if we consider, if we assume that this particular reinforcement is present inside the matrix material which is embedded inside the matrix material as shown here, thickness of matrix, thickness of reinforcement, then height. Like this, if we take into consideration and if we try to calculate here, then we will come to know here that 1 upon E2 is equal to 1 upon EF, TF. So this particular part also we have calculated during last lecture. For this step we have reached during last lecture. Here we have considered that 1 upon E2 is equal to VF upon EF plus VM upon EM. So transverse Young's modulus is calculated with reference to the properties of matrix and reinforcement and volume fraction also. In previous case, when that is considered to be a linear or longitudinal, at that time E1 is equal to EM VM EF VM. Is it okay? So EF VF plus EM VM direct addition was carried, but here while calculating the Young's modulus in transverse direction, because in transverse direction always that properties are weak. In longitudinal direction or linear direction properties are strong, but in transverse direction these are weak, and that's why 1 upon E2. So while calculating this Young's modulus in transverse direction, we are taking the reciprocal, and it is already proved during last lecture that 1 upon E2 is equal to Vf upon Ef plus Vm upon Em. Is it okay? Besides this, if we substitute here the percentage of volume fraction, is it okay? This Vf is nothing but volume fraction, which represents that small Vf upon small Vm, and small Vm, this capital Vm represents that small Vm upon small Vm. Is it okay? So like this, 1 upon E2 is equal to Vm upon Ef plus Vm upon Em. If we substitute here volume fraction of fiber, volume fraction of matrix, and the properties of fiber as well as matrix, then by calculating that values and taking its reciprocal, we will get the value of E2 here, and that value will be the Young's modulus in the transverse direction. So above example is solved once again here. In first example, with same material properties, when we calculated the Young's modulus, at that time value of Young's modulus which we calculated, we got as a 60 point. Here is the value 60.52. That was the Young's modulus in longitudinal direction. But same Young's modulus when we calculated in transverse direction with reference to matrix and reinforcement properties, we got this Young's modulus as equal to 10.37. Is it okay? So we should understand the difference between these two Young's modulus. What is E1 and what is E2? So as far as concerned with this E2, these values in transverse direction is small. So we can consider this 1/6 of capital U1. So how the difference in the properties we are observing in longitudinal and in transverse direction, that we can understand with this particular example here. Is it okay? Then that properties are plotted here in order to visualize the change with reference to addition of reinforcement. As reinforcement get added inside the matrix step by step, when reinforcement is 20%, when it becomes 40%, when 60%, 80%. Likewise, this 0 represents that there is no any reinforcement present. This is the pure material which is present on this particular y-axis. Is it okay? Here only matrix is there, and here only reinforcement is there. This side represents that there is only reinforcement. On this side there is only reinforcement, and on this side here there is only matrix material. Is it okay? So 0 represents that there is 0% of reinforcement. 0.2 represents that 20% of reinforcement, 40% of 60% of reinforcement. Now the percentage of reinforcement starts to increase. Here the property starts to become superior, and that means whenever that is equal to 1, that means 100% reinforcement is present here. So for 100% reinforcement, what are the properties of Young's modulus, that we know. Is it okay? So that change we are going to observe with percentage of reinforcement, and in longitudinal direction also, and in transverse direction also. Whenever we have seen this particular graph for longitudinal direction, the values of U was larger, but in transverse direction these are somehow smaller values. Is it okay? So that we can understand here. Is it okay? The ratio of diameter to fiber spacing like this. Now one more thing we are taking into consideration, that packing, fiber packing with this reference to here. Fiber packing means whatever the reinforcement present inside the matrix, because if that reinforcement is placed like this, is it okay? So we can understand this, the difference between this figure and this figure. Here we can see the that this D is the diameter of reinforcement particle. Because D is the diameter of reinforcement particle, and S is the space between these two. The space between these two reinforcement particle. Then by considering this D as a diameter and S as a space between that, and VF as a volume fraction of that, here we can identify the percentage of volume fraction VF. How to calculate the VM volume fraction? If we know the D and if we know the space between two reinforcement particles, then we can calculate the volume fraction. So this is true for circular fibers. Is it okay? This is true for circular fibers. Is it okay? Then if that is in a hexagonal structure, suppose this is in a hexagonal structure. Now what is the difference here? We can see in this case the particular fibers, these are present at corner of one square, but here these are present in hexagonal shape. Is it okay? Packing ratio will be larger in this case as compared to this case. In this case, packing ratio is larger. So square and hexagonal, this is the square packing geometry and this is hexagonal packing geometry. So this is the fiber packing or fiber spacing. In this case, this fiber space is lesser. In this case, that fiber space is larger. Is it okay? Diagonal shape, if we see here, in this case, if diagonal to diagonal we run, then we will come to know that this is the larger value in this case. But in this hexagonal array, this value is somewhat less here. Is it okay? So likewise, we can understand that fiber percentage is larger, definitely the properties will be superior, because the properties of the material is the outcome of percentage of fiber and properties of this matrix and fiber. So this is square geometry, this is hexagonal geometry, this is the fiber spacing, the diameter D, and yes, that relation is there. So circular fibers with hexagonal array and circular fibers with square array. These two differences we can understand here with this equation 3.42a and with this equation 3.42b. We can understand the difference between these two. When arrays are circular and at the same time when this fiber spacing is given by S and diameter is given by D, in that case for square kind of this structure, D by S is given as 4 Vm upon pi 1 raised to 1 half, and in this hexagonal array, that is D upon S is 2 under root 3 Vm upon pi raised to 1 half. So that we can understand with this figure B, and visualization has been shown with this figure 3.10 for strength of material approach or mechanics of material approach. So experimental data points are shown here for experimental data points, and for mechanics of material approach, because this mechanics of material approach which is shown here from this point here to this point here. Is it okay? So like this you can see that here we can see these points which are here. When 0% fiber is there and when 0.8% fiber is there, then by mechanics of material approach, how these properties are improving from this end to this end. Is it okay? Likewise, for experimental data points, if it is seen, because always any theoretical model, we should have to validate with reference to experimental results. Is it okay? And that's why when experimental results are validated with reference to this theoretical model, we should understand what percentage of difference is coming here. Likewise, here also for mechanical fiber volume fraction VF, here is also fiber volume fraction for VF. In first case, theoretical value of transverse modulus as a function of fiber volume fraction for boron epoxy unidirectional lamina, and that is comparison has been carried. And in second figure, means figure B and figure A, both figures are there. In both the cases, likewise, this comparison is made with experimental results and this theoretical model developed, which is strength of material or mechanics of material approach. Is it okay? So now with this, we will come to next calculation, that is the major Poisson's ratio. So how this major Poisson's ratio is calculated here? You can understand this major Poisson's ratio and minor Poisson's ratio. So first of all, we should understand the difference between these two things. What is meant by major Poisson's ratio and what is meant by minor Poisson's ratio? That difference, first of all, we should understand, and with that difference, we will proceed again. The major Poisson's ratio is defined as negative of ratio of normal strain in transverse direction to the normal strain in longitudinal direction. Is it okay? So transverse to longitudinal, this ratio, transverse to longitudinal, that ratio is considered to be major Poisson's ratio. Is it okay? So here we can understand this for composite material, this T represents in this equation 3.43 T represents the transverse. Is it okay? C represents composite. F represents fiber, and M represents matrix. Is it okay? So composite, fiber, and matrix. The deformations in transverse direction in the composite, the sum of transverse deformation in the fiber and matrix, that we can see here, we can understand here. Is it okay? So using the definition of normal strains, this particular strain, normal strain in transverse direction, if we see, change in length to the original length like this. So change in length is deformation, and deformation is given as by delta. Is it okay? So delta suffix F, that is with reference to fiber in transverse direction. Then TF is the thickness, means whatever the deformation is happened, that deformation is given by delta, and T is the thickness here. Is it okay? Likewise, in this case, this is the deformation for matrix. So deformation for fiber, deformation for matrix, and this one is the Young's the strain for fiber, strain for matrix in transverse direction. Is it okay? That we can understand here. So similarly, the strain in case of composite material. While calculating the strain for composite, strain for matrix, and strain for reinforcement or fiber, usual notations that are used for delta F, delta C, deformation of fiber, deformation of matrix, deformation of composite. That is all in transverse direction. And TF, TM, and TC represents the thickness. Is it okay? That is the original length for that composite. Is it okay? So transverse strain in composite, fiber, and matrix respectively. So substituting that values in 3.43, because this equation we know that deformation of composite is nothing but deformation of fiber plus deformation of matrix. Total composite deformation is definitely is the outcome of these two deformations, addition of these two deformations. Is it okay? So that values are substituted here. By substituting that values and with using the ratio VF is equal to minus, because already we have defined the major Poisson's ratio as it is the ratio or negative ratio of strain of fiber and strain of fiber in transverse direction to the strain of fiber in longitudinal direction. Similarly, this Poisson's ratio for matrix material, Poisson's ratio for fiber material, Poisson's ratio for matrix material. In both the cases, we are taking the ratio of strain of this fiber to the in transverse and longitudinal direction, strain of matrix in transverse to the longitudinal direction. Is it okay? Then Poisson's ratio is given as negative ratio of this composite material in transverse and longitudinal direction. Is it okay? So substituting all these values with the reference to these designations which are given here, and then taking here this Poisson's ratio value, what we can say, the Poisson's ratio is nothing but VF plus VM. That is the Poisson's ratio of composite material is equal to Poisson's ratio of reinforcement into volume fraction of reinforcement plus Poisson's ratio of matrix to the volume fraction of matrix. Is it okay? So likewise here we can identify the Poisson's ratio of the composite material. Is it okay? Now same example which is repeated. In this example, here you can see major and minor Poisson's ratio of glass and epoxy with 70% volume fraction. That is given here values. So we are getting like this value. Is it okay? Now next parameter which we have to identify the mechanics of material approach or strength of material is in-plane shear modulus. Is it okay? So shear modulus we know. The deformation of composite, again same formula which was used in 3.43 is repeated here. So deformation of composite is deformation of fiber plus deformation of matrix with reference to this figure. Then shear strain is nothing but the ratio which we are going to calculate. Shear strain we are calculating for composite material. Is it okay? So deformation to the So shear deformation to the shear thickness. Is it okay? Like this we are considering here, and with reference to that considerations, delta C is equal to gamma C TC, where gamma represents the shear strain. Is it okay? Gamma C represents shear strain for composite material. Gamma F represents shear strain in fiber. Gamma M represents shear strain in matrix material. Is it okay? Then thickness shear strength with regular notation shear modulus, the shear stress to the shear strength. So shear strength is equal to shear stress upon shear modulus. Is it okay? Similarly, shear stress in a shear strain of the fiber is nothing but shear stress upon shear modulus. Is it okay? Like this, if we try to substitute all the values here, then the shear modulus 1 upon Z2, that is to be calculated as Vf upon Gf plus Vm upon Gm. That represents again the shear modulus of the composite material is given as Vf, means volume fraction of fiber, upon shear modulus of fiber, volume fraction of matrix to the shear modulus of matrix here. Is it okay? So likewise, for the matrix material also we can calculate. The same thing we can calculate for fiber and matrix material separately. We all know this is the common formula which we have used in the second year also. That is shear modulus is equal to Young's modulus divided by 2 into bracket 1 plus Poisson's ratio. Is it okay? So this formula is used in order to calculate the shear modulus in case of matrix, shear modulus of fiber, and then finally shear modulus of this composite material. Is it okay? So this particular approach with which we are calculating longitudinal Young's modulus, transverse Young's modulus, in plane shear modulus, major Poisson's ratio, minor Poisson's ratio, density, weight, volume, all these things we have seen. So initially with rule of mixture, we have identified the volume percentage, weight percentage and density, and then by strength of material approach, we have identified the longitudinal Young's modulus, transverse Young's modulus, shear modulus, major Poisson's ratio and minor Poisson's ratio. Is it okay? So like this, we can have these different calculations here. Is it okay? Then with semi-empirical model here. Here we can see the semi-empirical model. So with reference to semi-empirical model, again longitudinal Young's modulus and transverse Young's modulus. So as far as concerned with our syllabus, we have mechanics of material approach and rule of mixture. So we are going to observe mechanics of material approach for the stiffness that we have seen, and then rule of mixture we have seen. Now we are going to see the elasticity approach. Is it okay? So this semi-empirical approach that is present, you should study this for getting the pure knowledge about this, how to calculate the properties of the composite material. For that purpose, this semi-empirical model, semi-empirical approach, that is very useful, and that is for those students which are going for performing their projects. For them, that will be very useful. But that part I will skip here, as we have to go for the elasticity approach. Is it okay? So for elasticity approach, we should use some of the terminologies, and that terminologies are very useful for us, that will be required for us. So as far as concerned with this elasticity approach, the first term which is associated is the elasticity model described are composite cylinder assemblage. Is it okay? CCA, composite cylinder assemblage, or CCA model. So that terminology is important with reference to elasticity approach. We should understand first of all that terminology, and then we should go for this particular model. So in CCA model, one assumes the fiber are circular in cross section and spread in periodic arrangement and contribution. So for that figure 3.18, which is given here, with reference to that figure 3.18, here the arrangement or uniform arrangement of the fiber inside the matrix is assumed here. Is it okay? For each and every type of mathematical model, there are certain assumptions. Here also it is assumed that whatever the reinforcement particle present or reinforcement present inside this matrix material, or whatever the fiber presents in that matrix material, so all these are circular in cross section and spread in periodic arrangement. Whatever the arrangement in between 1 2, that is arrangement same is repeated after one certain periodic times. Is it okay? So for that purpose we are taking the reference of this particular figure here. This is the periodic arrangement. Means suppose we take this particular bundle here, 1 2 3 4 5 6. Same thing is here, which is repeated. Same thing is repeated here. Same thing is once again repeated. Is it okay? So the distance between these particular two reinforcement particles, etc., that is also considered to be a periodic in nature. Is it okay? So this is the assumption in this particular case. Is it okay? Then here also we are considering the representative volume element. Is it okay? RVE is nothing but representative volume element that we are taking into consideration, and it is considered to represent the composites and respond the same. So the volume fraction of the fiber for that purpose, if we consider A as a radius of fiber, is it okay? And radius of matrix as a B, then A square upon B square. The volume fraction of fiber is considered to be a ratio of A square upon B square, where the radius of fiber is A and outer radius matrix is B. Is it okay? So with this particular figure we can understand here. So this reinforcement is present within the matrix. Is it okay? So composite cylinder assemblage. This term we are purposefully going to use here. Composite cylinder assemblage, CCA. So that's why how this cylinder looks. What is A? What is B? And how these figures are given here. That we should understand here. Is it okay? So with this today, with this particular part, I will stop here.